Hello and welcome to the talk on deep learning for characterization of deformation-induced damage. First of all, let me thank you for the opportunity to present this exciting topic. In this work, we focus on steel and why steel. Steel is and remains one of our most versatile materials. Important for industrial applications is in particular dual-phase steels such as DP800, which we analyze in our work here. This work focuses mainly on damage mechanism, and the better understanding of damage mechanism leads to a better understanding of processes or to build better processes, which in turn helps us to make better materials. So to understand damage mechanisms, we take a specimen, a sample of the DP800 steel in our case, and apply some stress. In the simplest case, we apply some uniaxial stress as shown here in the image. And then the traditional approach is the following. We take a panoramic image in the electron microscope and then look for potential damage sites. Once we have identified potential damage sites, we need to look at these manually. As you can see, we span more than 2 orders of magnitudes, which poses enormous challenges. So to gain a detailed understanding of individual damage sites is very difficult because the manual approach does not allow to analyze it statistically. And this is the key idea we want to pursue. We want to automate the image analysis using deep learning. So the key idea is the following. After we apply the stress, we obtain a high-res panoramic image in the electron microscope and extract automatically where potential damage site could be. This, at least potentially, leads us to tens of thousands of images. And these are classified to the type of damage we have using a deep learning algorithm. With these large number of images, we can then do a statistical analysis. Conceptually, it looks like this. We have the high resolution image and take small parts of it. Because we have so many of them, this leads us to a very large number of images. And this presents, first of all, a technical challenge. We have so many damage sites. It's okay to do this manually once for a proof of principle. However, if we want to do this more systematically, we need to not only develop the methods in terms of how we apply the strain on the material or how we classify them, but also set up an infrastructure to do this more systematically and have a large database of all those images. Another challenge is the definition of the semantic classes. In the manual approach, we would look for the potential damage site and look for maybe clear-cut cases of typical damage, such as margin site cracking, grain boundary decohesion, interface decohesion, or inclusions. And also, if you consult the relevant literature, we find many examples of how these different damage sites are defined. However, if we want to do this in a statistical way, we have to revise and clarify the class definitions. The definitions which are common in the literature are usually suitable for clear-cut cases, and this is what normally is looked at. But there are also many in-between cases or where it's not quite clear which damage mechanism it might be. But these are very important for statistical analysis. So the first step is to consolidate the class labels with multiple experts and agree on the semantic classes which we will then use to label the images that form the input of the training set for the deep learning algorithm. In the following, we focus mainly on margin site cracking, grain boundary decohesion, and interface decohesion, and we take out the inclusions in the preliminary step. As you can see, there's a large variation of the different images. This opens up the era of panoramic imaging, big data, and material science. The key step we want to perform in this automated analysis is to track the evolution of damages. That is, if we apply a little more strain repeatedly. We start with a pre-deformed one, the initial sample, and then do the panoramic imaging and the localization of the damage sites, and then apply more stress, 1.53% or 4.5%, and repeat the procedure. The next step is then to align the image and track how a specific damage has evolved over time, or rather has evolved with different levels of stress. If we want to automate the whole procedure using deep learning, it's very important that we verify that the performance achieved by the deep learning algorithm is at least comparable to the level of a human expert. As you can see, we've taken a few thousand of images at different levels of stress and verify that a human expert delivers the same performance as the deep learning approach. So this is an important key result, which enables us to do a statistical analysis to make sure that the output of the algorithm is comparable to what a human can achieve. However, if we look at the images, we face another challenge, and these are the image artifacts. These artifacts increase the chance for misclassification. In particular, we found that shadows of the electron beams on the 3D sample structure of the surface of the sample confuse the algorithm. So that means that we need to define different classes that extend the semantic classes. And for example, we added the class artifact shadows as a separate class. And doing this increases significantly the performance of the deep learning algorithms. So far, shadows remain the major artifacts, but we need to monitor, of course, if we had different kind of preparations, different samples, or even different electron microscopes. That also implies that data doesn't speak for itself. It's not that we can just look at the images and put them into the machine learning algorithm. We need the human expertise to interpret what we see. One of the biggest challenges in training neural networks is that we need lots and lots of images. And this is the main challenge, that we need to create the image labels, even after we've defined the semantic classes. Supervised learning is the most accurate approach for neural networks and deep learning, but it requires labeled images that are representative of samples for the later inference. But these are very costly to obtain because, as we've just discussed, they need to be created manually by experts. And also, if we do this once, this is a challenge for generalizability. For example, in the first work, we work with uniaxial stress on the sample, but of course we want to extend this to different structures such as biaxial stress. A very successful approach is here to use traditional image augmentation, such that we rotate the image, that we use pixel dropout, blur, and share to simulate how different images could look like under different strain paths. On the left, in image A, you can see the original image, and then on B, we apply a random rotation. And this is then what's fed into the network. B, C, B, D, and E are the different types of pixel dropout, Gaussian blur, and random share that also help to generalize the network. They represent different kind of artifacts that could lead to impairment in the training, such as, for example, that the electron beam is not quite in focus and it looks a bit blurred. So where do we go from here? First of all, we already mentioned that there's a significant technical challenge we have to address. If we want to do this more systematically, we have to find a way to handle all this big data. Unfortunately, there isn't an established community-wide infrastructure available, and a promising candidate to start working with this is MongoDB. It's a mature technology, it's open source, there's a community and an enterprise solution, and can be scaled to a global scale. And we don't only have to handle the data itself, these are the images, we also have to store the metadata, the data about the images, alongside with the data. So this starts at very simple things like date, time, and location, and the sample ID. But also we have to capture the experimental conditions under which we have obtained the image. First of all, that means the sample itself and how it was prepared, and the strain path and the etching maybe, and also then the conditions and the setup of the electron microscope, the settings, the different types of electron microscopes, the beam settings, and so on. And because we start with a panoramic image and then cut out the small images, we have to keep the relation of how the small image fit with the large image, the panoramic image, together. And we need to keep track of all of this data and the metadata, so that we can reproduce the results as well. Beyond this sort of technical challenge, we also have to think about how we can refine the algorithms we use. As we said earlier, supervised learning is great in terms of accuracy because we have labeled images and the labels have been done manually by an expert. But we also have seen that, for example, data doesn't speak for itself. We need to verify the semantic classes, which again needs the expert. And we need to include all the expert knowledge, not only for the semantic classes, but also for the image artifacts. Unfortunately, this doesn't scale. New data needs to be labeled manually in this approach, and it doesn't get any faster with time because still the expert needs to do it. And additional people means more training. So in order to scale this up, we need to explore different approaches such as deep clustering, self-supervised, semi-supervised, semi-supervised, contrastive learning, and we'll discuss this in the next few slides. There are many approaches in the machine learning community, but it's not quite clear how they would apply to the field of material science. Let's start with deep clustering. This is a potential avenue which we should explore, and it sort of combines the ideas of neural networks in terms of representation learning and clustering. The idea is that we use convolutional neural networks, as we've done before, but then don't use them to classify, but we use them to extract the features of the images, sort of the knowledge of what we see in the images. And then once we have these features, we can use a clustering to find similar images and group the images into classes. This, at first glance, sounds very promising. And as you can see from the references below, there are many recent works in the field of computer vision and machine learning that focus on this approach. It has the advantage that little to no labeled data is required because we essentially do clustering, but it has the disadvantage that convolutional neural networks are in general not explainable. And in our work so far, we've seen that the decision boundaries produced by the convolutional networks are not quite what expert would draw. It's also a high risk and a hard to control risk as well, that such an approach learns more the image artifacts instead of semantic classes. And this is a number of clusters. This is a free parameter. This doesn't really matter so much if we have maybe a few hundred or a few thousand images, but if we think about having hundreds of thousands of images, it's not quite clear how we would set the numbers of clusters, because there might be many different kind of damage types which we really haven't thought of, or they are so in between that they can't be really grouped well into a class automatically. So this is something which is very challenging with this kind of approach. But as we've seen, there's a lot of work going on in the computer vision community, and somewhat independently in the material science community. First work has started as well. Another approach is semi-self-supervised, semi-self-supervised learning. And the idea behind these kind of approaches is that we want to reduce the dependency on labeled images. We don't want to sort of get rid of the labeled images per se, but we want to work with less labeled images. And the general idea is that we split the task into two steps. We have a pre-trained network with a suitable pretext task, as it's called. And then we have a fine-tuned network, which is what we use the labeled images for. And the idea of the pretext task is that this is something we can explain, and which is something a human could do, but it's also a task that the computers can do without human input. So the idea is that the pretext task learns the general representations in the images. And the idea is then that if we have learned this pretext task, we don't need so many labeled images for the further downstream fine-tuned network. And you can see some examples here on the right-hand side. And in computer vision, we mainly deal with everyday objects, for example, a dog. And a typical pretext task is to learn how to fill the gap. So I put a black square where the nose would go for a dog. And we can very well imagine how the complete image would look like. But if we look at the Martin-Side crack in material science, for example, it's not quite so clear. Yes, from the schematic you see above, you would say that there's a Martin-Side crack, but the islands of the Martin-Side could go differently. And because this is a mainly stochastic process, how these islands are formed, it's not that we have always a crack in the middle that we can learn from, whereas in the case of the dog, we always have a nose in the spot. Another typical pretext task in computer vision is to learn the placement. So we cut out several parts of the image, let's say the nose and the eye. And because faces always look sort of the same way, and the nose is always in the same spot, and we really don't swap eyes and nose, it's a typical pretext task the network can learn, because it knows that it shouldn't place the eye where the nose goes. However, again, for the material science case, it's not so clear if you couldn't have a different kind of damage mechanism, and there isn't a natural order in these images. So the main challenge in this approach is that we need to define a suitable pretext task for the electron microscope imaging application. And it's not quite clear if the approaches used with everyday objects would work equally well with our case here. And also there is a high risk that the networks learn maybe image artifacts or specifics of the imaging equipment rather than the content of the image. However, it's a very promising approach, and it reduces, at least potentially, the number of labeled images we have. An interesting variant of this is contrastive learning, and that works by maximizing the similarity or the difference between image pairs, and that also would help to reduce the dependency on labeled images. Within the computer science community, people have looked at these approaches and see that in general, it's a very promising avenue, and for these everyday objects, as little as one image is sufficient, and they have found combining with these self-supervision and data augmentation to learn sort of the lower layers of the neural networks, so the more general structures, but it's difficult. In particular for the deeper layer, for the fine-tuning layer, self-supervision remains inferior even with everyday objects, even if you have lots of images. So we will not likely not be able to do away with labeled images at all. And as we've said earlier, we need to investigate if the approaches used in computer vision really work well within the realm of material science. This already brings me to the end of the talk. And as we've seen, deep learning opens the door to statistical analysis in material science, and this is very exciting. We can start to do large-scale damage identification with high accuracy, and this in turn enables us to do a statistical analysis and the evolution of damage. However, significant challenges remain. One of them is the class definition, the semantic classes. We need to understand the underlying dominant mechanisms better, in particular for damage evolution, to define the semantic damage classes. And then also we need to be clear of what kind of artifact classes we need to include. And we have purely technical challenges to set up an infrastructure which allows us to handle this big data type of thousands and thousands of images and the according metadata. And then if we want to go beyond supervised learning, we have to be aware of that it's unlikely to be fully replaceable, at least in the near future. But there are many potential avenues which might be able to help us to avoid the prohibitively large cost of manually labeling so many images. So it is that we are at an exciting opportunities for material science to enter the age of large-scale statistical analysis as well. So thank you very much for your attention.